All right, guys, in this video, we're going to look at new ways of calculating our heat of reaction. And here we're calculating delta H naught. So anytime you see that degree symbol, it is representing delta H naught. And what that degree symbol means is that we are under standard conditions for our reaction. And standard conditions, if we're dealing with a gas, it means we're kind of under ideal conditions. So we're going to be at that standard pressure of 1 atmosphere. If we're dealing with solids and liquids, they are going to be pure, so they're not going to be mixtures. If we're dealing with solutions, we're going to say that they are at 1 molar if we are under standard conditions. And temperature-wise, we tend to be about room temperature, which is that 25 degrees Celsius. So we will kind of have to account for those, and those temperatures and pressures may show up later on in other calculations. But understand that degree symbol means that we're under standard conditions. There are going to be 3 ways for calculating delta H naught. The first one is going to be using heat of formation values. These are values that are in a table in your textbook, or they will be provided for the specific questions and the specific substances that you need. We're also going to be looking at learning Hess's law. This deals with some of those reactions that have mechanisms where it's multiple reactions that combine to make the overall reaction. And then we can also find delta H naught by using bond dissociation energies. This is going to look at the energy from bonds broken and bonds formed throughout the course of a reaction. So let's look at heat of formation first. So this looks at the change in enthalpy that accompanies formation of 1 mole of a compound from its elements with all substances in standard states. Now note that this produces 1 mole of a substance. So if it is a reaction that produces 2 moles, it is not a heat of formation reaction. If it has compounds that produce 1 mole of a substance, it is not a heat of formation reaction. It has to have elements forming that compound and only 1 mole of that compound. So you might have a heat of formation reaction. Typically, like when we produce water, so hydrogen, oxygen combine to make water. And balanced reaction-wise, there are 2 waters and 2 hydrogens. This would not be a heat of formation reaction. This would have to be simplified to only produce 1 mole of water. So we would have to cut all of our coefficients in half. So this is an instance where you may see coefficients that are fractions if they are heat of formation reactions. So you may just be asked to recognize which of the following is a heat of formation reaction. We can actually calculate the values of heat of formation reactions. Something to note is the value for a free element in its standard state is 0. So if you have elemental oxygen or elemental iron, the value will be 0 for those. But we will have certain values for compounds. And like I said, that will be in a table in your textbook, or it will be given in context of a specific question. So heat of formation values are in Appendix 4 of your textbook, which is near the back, but not all the way at the back. I believe it's page A5 they start at. Those are going to be different values depending on which compound we are dealing with. So let's look at how this is. To find heat of formation, or heat of reaction from heat of formation values, we have to do the sum of the heat of formation of the products minus the sum of the heat of formation values for the reactants. And you are going to have to account for coefficients in these. But to find the overall heat, you're looking at the products minus the reactants for these. So let's look at this example. If we want to calculate the enthalpy change, remember enthalpy is just heat. So calculate the enthalpy change for the oxidation of iron 2 oxide into iron 3 oxide. And here it gives us the equation of we have 4 iron 2 oxides and oxygen producing 2 iron 2 oxides. So if we're looking at the heat of the reaction, remember we said heat of reaction is the sum of heat of the products minus the sum of heat of the reactants. So whenever we actually lay this out, we have our product is the iron 3 oxide, and note that there are 2 of them. That is our only reactant, or excuse me, our only product. So that whole thing is going to be our sum of our products. That subtracts the sum of our heats of reaction for the reactants. Notice that oxygen is an element. Its heat of formation value will be 0. So we can ignore oxygen here, but our other reactant is the iron 2 oxide, and there are 4 of them. So we need that total sum, and that will be the sum of our reactants. Like I said, these values are in that appendix in the back of your textbooks, but these will typically be given in a table or in context with the specific questions. If we look in the back of our textbook, the value for iron 3 oxide is negative 824.2, and that's kilojoules per mole. So we would need that total to be the sum of our products. Iron 2 oxide, when we look in the back of the book, is negative 272.0 kilojoules per mole. And since we're multiplying by the number of moles, our answer ends up in kilojoules ultimately. So simplifying this, you can put this in the calculator as is, but the sum for our products would be 1,648.4 kilojoules. The sum for our reactants would be negative 1,088 kilojoules. And whenever we add these together, it's going to be negative 560.4 kilojoules. And since all of these are constants from our textbook, we're not going to round with these. We're going to leave it as is because we're dealing with constants. So let's look at another one following the same kind of pattern. We're going to calculate the heat of reaction for the following process. And we have sulfur dioxide with water making sulfur trioxide. So yet again, we have to do the sum of heat for the products minus the sum of heat for the reactants. So our product is the sulfur trioxide, and there are 2 of them. That's our only product. That is going to subtract the sum of heats for our reactants. Well, we have sulfur dioxide, and there are 2 of them. And then we also have oxygen. Remember, that will be 0, so we don't have to include that whenever we're looking at it. When we use the values from our textbook, sulfur trioxide is negative 395.7. Our value for sulfur dioxide is negative 296.8. So simplifying is going to be negative 791.4 kilojoules for the products. The reactants will be negative 593.6 kilojoules. So when we subtract that, we get negative 197.8 kilojoules. So this would be an exothermic process overall because it is releasing heat. All right, so let's look at Hess's law. Like I said, Hess's law is very similar to looking at our mechanisms like we did in kinetics, where there are multiple steps to make up the overall reaction. So with Hess's law, the heat of reaction is going to end up being the same, whether it takes place in one step or a series of steps. So if we want to know the heat of the overall reaction, we can combine the heats of reaction for the individual steps that make up that overall reaction. This is true because enthalpy is a state function. That means it does not change based off of outside conditions. So let's look at how this works. Here we're going to determine the heat of reaction for the following reaction. We have copper 2 oxide and hydrogen producing copper and water. And it gives us two different thermochemical equations. The first one has copper 2 oxide making copper and half of an oxygen molecule. And it gives us the heat of reaction for that specific reaction. And then we also have water producing hydrogen and half of an oxygen molecule. And we have the heat of reaction for that one as well. We're going to have to look at how can we use these thermochemical equations to get our overall equation. And you may have to flip a reaction and reverse it. You may have to multiply a reaction by a factor. And anytime you change the reaction, it will change our delta H value in the same way. So looking at the first reaction that was given with the thermochemical equations. The copper 2 oxide making copper and half of an oxygen. If you notice, we have a copper 2 oxide on the reactant side in both reactions. We have copper on the products in both reactions. And the coefficients are the same, so we do not need to change that reaction at all. But if we look at the second reaction, that's water producing hydrogen and oxygen. Notice that water is a reactant in our thermochemical equation and a product in our overall equation. So that means that this reaction is reversed. So we need to flip this reaction. So I'll rewrite it flipped. So we have H2 plus half of an oxygen produces water. And what happens is if we flip the reaction, it changes the sign of our delta H equation. So it is now going to be negative 242 kilojoules. So I'm just going to mark out that original one so I don't get confused. Now we have water on the product side. We have H2 on the reactant side. And if we were to add these together, the half O2s would cancel, meaning they are not in our overall reaction. So we have rearranged the equations in the order that we need them. So what we do at this point is we now add together the delta H values to get the overall heat for the reaction. So these added together would be negative 87 kilojoules. So this whole process would still be exothermic and would produce the same amount of heat whether it was done as one step or in multiple steps. Let's look at another one. This one's a little bit trickier. Here we have magnesium oxide and hydrogen chloride gas producing magnesium chloride and water. So here we have three thermodynamic equations, and we need to see what we need to do to these equations to make sure they can equal our overall equation. So from the first thermochemical equation that's given, magnesium is not in there at all, so we're hoping it will cancel at some point in time. But we have 2 hydrogen chloride gas as a reactant, 2 hydrogen chloride gas as a reactant. So, and we have 1 magnesium chloride as a solid, 1 magnesium chloride as a solid. So we are not going to have to change that reaction at all. So let's look at another one. I'm going to change to red for the second equation. Looking at the second equation, we have magnesium, which is not in our overall reaction. Half an oxygen is not in our overall reaction. But we have this magnesium chloride, or magnesium oxide, that is a product. But in our reaction, it is a reactant. So this reaction will need to flip. So I'm going to rewrite this down below. So if we have the magnesium oxide plus magnesium plus half oxygen, and remember that means that we are going to have to change the sign of our delta H value. So I'm going to mark that one out since we changed it. So now the magnesium oxide is in the correct spot and it has the correct coefficient. So we're not going to have to worry about that. I'm going to swap to green for the third equation. Looking at the third equation, we have water producing hydrogen and half of an oxygen. Water is a reactant in the equation given, but our overall reaction, water is a product. So this reaction also needs to flip. So we're going to have hydrogen plus the half oxygen producing water. That also will change the sign of our delta H value for that reaction. So that will cancel out. And notice that now water is on the product side and is the correct coefficient. We know these are going to add together correctly because now we have magnesium on the product and reactant side that will cancel. And we have the half oxygen on the reactant and product side that will cancel. And hydrogen on the reactant and product side that will cancel. So everything else that we needed is left behind. So now that we've rearranged it properly, we can add our delta H values together. And I'm using the ones that I wrote. That way I changed the sign of them. When we add these together, it should be negative 141.1 kilojoules. Now, we're going to do another example that is also a little bit tricky, but we are going to do an example where the coefficients do not match, whereas in this one, all of our coefficients matched once we flipped the reactions. So let's look at this one. We have 2 carbon in the graphite form reacting with hydrogen to produce ethine, the C2H2. And we have 3 thermochemical equations, and we need to see what we're going to do to them to get our overall equation. So notice that we do have graphite on our reactant side in both reactions, but in our overall reaction, there are 2 graphites, whereas our thermochemical equation only has 1. So we are going to have to multiply this reaction by 2, meaning we are going to multiply our H value by 2 as well. So if you multiply the reaction, you also have to multiply that delta H value. When we multiply that, this is going to change to negative 787 kilojoules. And I'm just going to put a 2 in front of all of our substances. That will help us out a little bit. Looking at the second reaction, we have hydrogen as a reactant and hydrogen as a reactant in our original one. And they are the same coefficient, so we don't have to change that second reaction anymore. But if we look at the third reaction, we have 2 C2H2s as a reactant, and we have 1 C2H2 as a product in our overall reaction. So we have to flip this reaction, and we have to divide by 2 because we need the coefficients to match up. So I'm going to rewrite this flipped and divided by 2. So it's going to be 2 CO2s of water producing a C2H2 and 2.5 oxygens. Now, since we flipped the reaction, that does change our sign of delta H, and since we divided by 2, we also have to divide this by 2. So our new delta H value for this reaction is going to be 1,299.4 kilojoules. So I'm going to mark out that equation so that I see my redone one. We can always double check that it is going to cancel out properly. So we have 2 CO2s in the first reaction and in the third reaction on both sides. Water, in the green one, we have 2.5 waters. We have 2 from the first one and half from the second one. So those will cancel. Or excuse me, oxygens, not water. We have water will cancel from the second and third reaction. And then everything else that is left is correct. So we can now add together our heats of reaction. And this is going to be 226.6 kilojoules. So this is an endothermic reaction. It requires energy for it to occur. So that was looking at Hess's law. And like I said, be careful that the substances are on the correct side. Are they on the reactant side or product side? And make sure your coefficients match with those. The third way that we can solve for heat of reaction values is by looking at bond dissociation energy. So there's energy stored within bonds. So energy is required to break a chemical bond. So energy is used to break a bond and is released whenever a bond forms. So we're going to be looking at the energy used to break bonds compared to the energy used to form those new bonds. So for heat of reaction with bond dissociation energy, and this is different than the other heat of formation one we did. We're going to look at the bond dissociation energy for the reactants minus the bond dissociation energy for the products. So this one, the reactants and products are switched because we're looking at the energy used whenever the bonds are broken versus released whenever the bonds are formed. And that's the difference we're looking for. And they updated our textbook. So there is a table of bond dissociation energies on page 422 of your textbook. And you do have to pay attention to the actual structure. Is it a single bond? It is a double bond or a triple bond? Because remember, triple bonds are stronger. It requires more energy to break apart a triple bond than it does a single or a double bond. So these you may have to draw out the structures. That way you know what bonds are being broken and formed. So let's look at a problem with this. And yet again, like I said, these are in the textbook on page 422. In terms of an actual problem, like on a quiz or a test, you would be given values to use for these. So looking at this reaction, we have ethene producing ethane whenever mixed with hydrogen. And notice the way that it is drawn out. This is a very basic dot structure. You may need to expand this. But it does tell us we have a double bond in the first structure. So this is a carbon with 2 hydrogens, double bonded to another carbon with 2 hydrogens. That is with hydrogen, which remember has a single bond. And that is making the ethane, so the carbon with 3 hydrogens, single bonded. If it doesn't show a double or triple bond, you assume it's single bonded. Go into a carbon with 3 hydrogens. And like we said, we're going to be doing the energy of the reactants minus the energy of the products for this one. This one is backwards. This is the only one that we do reactants minus products. So we're going to have to take into account what specific bonds are being broken for the reactants. So in the reactants, we have these CH bonds that are single bonded. And if you count, there are 4 of them. So we have 4 CH bonds. We have this double bonded carbon to carbon. And then we also have this single bonded hydrogen to hydrogen. So those are all of the ones that are on our reactant side. Remember, that is going to subtract our product side. Sorry, there's an announcement.
Please take your things and go to the cafeteria at this time. You will remain in the cafeteria until time for dismissal.
So
those students who plan
we
to
have
purchase lunch,
those
take
single
your
bonded
things
carbon
with you to the
hydrogen bonds.
cafeteria so that you can purchase lunch and remain there until
And there are
dismissal.
6 of them. And we also have this single bonded carbon-carbon. Sorry about that. So these are the values that you would be given or look up in your textbook. So I went ahead and looked them up in a textbook. Our carbon to hydrogen single bond is 414 kilojoules. And like I said, remember there are 4 of them. A carbon double bonded to another carbon is 611. Hydrogen single bond to hydrogen is 436. So that would give us the total for our reactants. On the product side, that carbon single bonded hydrogen was 414. Carbon single bonded to carbon is 347. So we would get that total for our products. And we could have simplified this whenever we have the same number of bonds on both sides. But people tend to make mistakes sometimes doing that. So our total for our reactants is 2,703 kilojoules. Our total for our products is 2,831 kilojoules. So whenever we subtract these, it is negative 128 kilojoules. So this overall reaction would release energy. More energy is going to be released when the bonds are formed than we're used to actually break those bonds. So those are the 3 different ways that we can calculate heat of reaction from those. And we'll do some practice problems with this later on.